Alright, so today we're going to be talking on an important method to do integration, and it's called integration by substitution. And the idea behind this is, so far we have kind of seen the integrals of common functions, like for example, if I had x to the power 4 dx, you guys would know that this is x to the power 5 divided by 5 plus c. And that's because this form takes the form of a power function, and we know what the integral of that is. But what if we have a function that doesn't quite take up that form? Like for example, we have the square root of 18 minus x squared or something like that, right? It doesn't really take up that form. But sometimes we can still find the integral of this by transforming this into a form we're familiar with and then integrating that function. To make this all concrete, that transformation process is called integration by substitution. And the best way to learn this is we just do a lot of practice problems, so that's what we're going to be doing. So let's just get right into it. Problem 1. Evaluate the integral of x plus 2 to the power of 5 dx. Now, one way you could do this is literally evaluate x plus 2 times x plus 2 5 times, and then whatever polynomial you have, we integrate each term, but clearly that's probably not the best way to do it. So how do we get this into a form we can kind of manipulate and we're familiar with? What if we substitute in a variable for x plus 2? So let's call w is equal to x plus 2, and that's the whole idea behind integration by substitution. We basically rename some of the terms inside of the integrand into a variable that helps us evaluate the equation. So now we have renamed and changed our variable into w. So we have the integral of w to the power of 5. But the problem is we cannot have the variation as dx because now we're in terms of w. But we can find a relationship between dx and dw by simply taking the derivative of w, and we know that dw is simply equal to dx, since if we remember differentials, that's basically how you'd get that. And so now we can also have dw over here, and we know this is the form of a power function, so this is simply equal to w to the power of 6 divided by 6. And since the original problem was in terms of x, we have to substitute in back x. And we know x or w is equal to x plus 2, so we can substitute that value in. So we get x plus 2 to the power of 6 over 6. And notice how much more simple this was than the alternative of us evaluating x or multiplying x plus 2 5 times. And then obviously we should remember the plus c because it's an indefinite integral. So that was a basic problem. Let's continue. Problem 2. We want to evaluate the integral of the square root of 4x minus 1 dx. Now, we know a function that we know the integral of is like the square root of w. So let's try to go around doing a substitution that makes us get that value. The whole underlying idea of this whole process is to get us to a form that we're similar with and is easy to manipulate, like the square root of w. So that suggests that we can make the substitution of w is equal to 4x minus 1. In this case, dw is equal to 4 times dx, because if we take the derivative with respect to x here, for like each change in w, x is changing like 4 times, right? So that's how we get dw is equal to 4 times dx. And then our integral problem just becomes the square root of w. And then dx is, or dw is 4 dx. And over here we had dx, right? So dw over 4 is equal to dx. And then we substitute in that value for dx, so dw over 4. And so the new thing that we're solving is simply the integral of the square root of w divided by 4 dw. And so we can remove the 1/4 because that's just a constant. And then we can integrate square root of w, which is just w to the power of 3 over 2 times 2 over 3, which then is equal to w to the power of 3 over 2 divided by 6. Now we substitute back in the value for x, or the value for w, which is 4x minus 1. So we end up with 4x minus 1 to the power of 3 over 2 divided by 6 plus c. And in this case, there's really no other way for us to evaluate this with the tools we already know without using the substitution, because there's no way for us to expand out this term like we could have in the previous problem. So with this problem, we really see how powerful integration by substitution is, and it's almost required to solve complex integrals, as you keep finding different integral formulas. So let's just keep trudging along this road, and then we can mix in other non-polynomial functions. So problem 3, integrate the cosine of 7x plus 5 dx. And we know that we kind of know what the cosine x dx integration is, so the obvious substitution is to remove the 7x plus 5. So let's call 7x plus 5 is equal to w. Also, just a side note, this substitution is often called u-substitution. And the reason it's called that is because the change of variable that is made is often called u. I'm just using w because I think u is a confusing variable, because u's and v's, at least my u's and v's, look very similar. So that was just an aside. But this is equal to 7 dx is equal to dw. So we found the relationship between dw and dx. The next thing we do is simply perform the substitution. So now this becomes the integral of cosine w, and then dw is simply dx is simply dw over 7. So we substitute in that value for dx. And now we have ended up with the integral of cosine w over 7 dx, or dw, sorry. And we know how to find the integral of that. That is simply sine w divided by 7. Substituting back in the value for w, that is simply equal to sine of 7x plus 5 divided by 7, and then plus c, because this is an indefinite integral. Let's move on. Problem 4. Find the integral of 1 over cosine squared 2x dx. Now right off the bat, we don't really know, one substitution you could think of is substituting in the value for 2x, but we don't really know the integral of 1 over cosine squared 2x, right? But we can use the properties of trigonometric properties to rewrite this as secant squared 2x dx. And now we know that the secant square x is simply the derivative of tangent x, so we can see an obvious substitution now is w is equal to 2x, therefore dw over 2 is equal to dx. I'm just skipping this middle step now because we've seen it multiple times. So after a substitution, we get secant squared w dw over 2. And then that's the same thing as 1/2 tangent w, which is the same thing as 1/2 tangent 2x plus c. So really, integration by substitution is just, the hardest part is finding the correct substitution, and after that, the steps just follow doing like us doing normal integration. And so the hardest part is finding the perfect substitution. And I think the only way you get better at that is just by looking at a lot of different integrals and evaluating them. So the best way is just through practice. And so let's just keep moving on. Problem 5. Integrate tan x dx. Now, we don't know anything about tan x besides the fact that tan x is equal to sine x divided by cosine x dx. And now, a substitution that we can do is if we substitute w is equal to cosine of x, notice how dw is equal to minus sine x dx. And that's the same thing as this numerator over here. So now, like, this problem is unique in the sense that we've never seen like an extraneous term that can also help when we're trying to substitute in the value for dw. And over here, the substitution we made perfectly helped us get rid of that sine x and the dx. And so usually, like, substitutions don't only have to do with getting rid of the dx or just like the term that you're substituting in for. It can also help get rid of these extraneous terms like sine x. And so we know that minus dw is equal to sine x dx. And now we have everything to continue on. We can rewrite this as minus, coming from that minus dw, 1 over w, because that was our substitution, dw. We know that this evaluates to minus ln absolute value of w plus c. And then that is finally minus ln absolute value of cosine x plus c. And if you want, you can rewrite this as ln of 1 over absolute value of cosine x. This is just coming from the properties of logarithms. That's the same thing as ln of absolute value of secant x plus c. So either one works. It's really just up to you. And so what we have continually done, right, like in all of these problems, is really we have taken 3 steps, right? We have seen that our function, or like the integral, is in some form of f of g of x times g prime of x dx, right? This g prime of x dx comes from the fact that once we make that substitution to take away g of x, we have to also write how that new variable changes, and that's just g prime of x dx. And we make the substitution of u is equal to g of x, and we get that du is equal to g prime of x dx. And then we're able to rewrite this whole thing as f of u du, and hopefully whatever new form we have this in is like something that we know how to integrate. And so once we've integrated that, we get some integral, which is some f of u plus c, and then we convert that into some, like, I don't know, capital G of x plus c by substituting in the value of u. So the reason why I didn't start off with this is because this is very general, and honestly, like, this whole process doesn't make much sense until you actually have seen concrete problems that utilize the substitution. So yeah, that was a bit of an aside. We can keep continuing on with problems. I think this is problem 6. Let's find out the integral of x squared plus 2x plus, or x squared plus 2x minus 3 squared times x plus 1 dx. I think just looking at it, it seems that we should probably get rid of like these two terms together. And one substitution that seems kind of reasonable is to make w is equal to x squared plus 2x minus 3. we then get dw is equal to 2x plus 2. And that's the same as, or 2x plus 2 times dx. And that's the same as dw is equal to 2 times x plus 1 times dx. And therefore dw divided by 2 is equal to x plus 1 times dx. And then now we can continue on with our substitution. So this is equal to the integral of w squared divided by 2, coming from this dw over 2, times dw. And we know how to evaluate this. This is the same thing as w to the power of 3 divided by 3 times 2, which leaves us with w to the power of 3 divided by 6. And then re-substituting in, writing in terms of x, we get x squared plus 2x minus 3 to the power of 3 divided by 6 plus c. Alright, problem 7. Find the integral of sine to the power of 4x times cosine x dx. That is equal to u to the power of 4 du. Or, sorry, I just skipped to the next step. Alright, sine to the power of 4x times cosine x dx. We know that the derivative of sine x is cosine x, so like a pretty obvious one is just w is equal to sine x. And so dw is equal to cosine x dx. That gets rid of this whole thing. And then we're left over with w to the power of 4 times dw, which is simply w to the power of 5 divided by 5 plus c, which is equal to sine x, or sine to the power of 5x divided by 5 plus c. So these have been indefinite integrals. What if we have a definite integral? So when we have definite integral, the process remains much the same, but there's an ability to shortcut the steps. And to illustrate what I mean by that, let's just look at this problem. The integral from 0 to pi over 4 of tangent x times secant squared x dx. We know that the derivative of tangent x is secant squared x, so that tells us that our substitution is probably going to be w is equal to tangent x. Therefore, dw is equal to secant squared x times dx, right? And so we can rewrite this as w times dw. But notice how I did not fill out the limits, right? That's because these limits are in terms of x. So x is equal to 4, x is equal to pi over 4. But when we write stuff in terms of w, our limits change. And so here we really have two ways we can go about solving this problem. We can find the formula for the integral of this and then proceed as we did before. So what I mean is we can ignore the limits for now, and we know that the integral of this is w squared divided by 2. And then when we resubstitute in the value for w, we get tangent squared x divided by 2, and then we evaluate it between 0 and pi over 4. And therefore we get tangent of pi over 4 squared divided by 2 minus tangent of 0 divided by 2. Tangent of pi over 4 is 1, and we know that tangent of 0 is 0, so this is simply 1/2. So that's a valid way of doing it, and I'll call this arrow path 1. But sometimes we get this step of finding the integral, resubstituting, or re-expressing in terms of x, and then solving for this, and then solving the integral might take longer than this other path, where we just re-express everything in terms of w. And sometimes it's just easier to evaluate the definite integral when it's in terms of this new in terms of the new variable. What I mean is, before we had x is equal to 0 as our lower limit and x is equal to pi over 4 as our upper limit, and we know that through our substitution w is equal to tangent of x. So tangent of 0 is 0. So our lower limit in our new variable, when everything's in terms of w, is 0, and tangent of pi over 4 is 1, and our upper limit is 1. So we have found the definite integral in terms of w completely, and so once we evaluate this integral, we can just do w squared divided by 2, and we don't have to do the re-expression in terms of x because we've already re-expressed our limits in terms of w, and so we can just continue evaluating everything as if we were evaluating this definite integral. And when we do that, we get 1 squared divided by 2 minus 0, and that's simply 1/2. And you could argue that if because we did not have any trigonometric functions here, it was easier to evaluate and less prone to making error when we did the re-expression than this first original path where when we resubstituted in terms of x, we had to still deal with trig functions. So it's really up to you. Both paths will lead to the same solution at the end, but with u-substitution on definite integrals, you now have two ways to solve for that definite integral. And so that was u-substitution. Hopefully the numerous examples at least helped with building intuition and how to solve definite integral or integrals that require substitution.